What I'd like to do is start the design challenge by looking at the questions that were asked. The speakers especially were asked to have comment on this and actually add slides to their talks to address some of these questions. And what I'd like to do is we're going to start off by just introducing the questions. You can all be thinking about them. Then I'd like to have the speakers who remain here. Oh, and if there are any questions we have of the speakers that we want to introduce into the record as particular questions, then that should be done. And then what I'd like to do is have the speakers comment. And then what I'd like to do is, I'd like to actually, how many do we have in the room? Okay, we'll just do one group. So Adrian Dove, who's the co-chair, will be taking notes. I will be leading the discussion session. As I said, we'll start off with the speakers themselves making comments. Are there any further questions about the talk? I would like to introduce two things. Some of them were alluded to. One of them basically is when you're doing the simulations or modeling, how you look at night and day. So how you simulate night and day on an asteroid. I mean, there obviously are very different considerations for night and day on an asteroid than there are on the moon, and what role that plays in what happens to the dust, what happens to hopping or wafting of dust. And also, when we talk about hops, since we don't really think that there's too much horizontal transport based on some other evidence, what we're talking about in the way of horizontal hops, if any, or we're just mostly vertical.
Okay, so the biggest difference between an asteroid and the moon, I would say, is the length scale. So on an asteroid, you can have global transport, global phenomena come into place, whereas on the moon, you could basically treat it as a planar patch. So unless your dust is lofted to a very high altitude on the moon, you're just over an infinite surface, and you've got simple geometry, you're at night side or your day side or terminator where things might be more complex. But over a small asteroid, something could be lofted off the day side and then find itself basically very easily or quickly on an orbit where it's going through more complicated sort of global dynamics. The question about horizontal transport, and I'm not sure what you're thinking about in terms of the evidence about how much there is or isn't. I guess I would say the only evidence we have that there is the presence of the pons on Eros. And so we modeled that, and this was with a student of mine, Anna Hughes. So Hughes et al., 2008, modeled the dust pond formation two different ways. So both with the same physics, but two different numerical approaches. So the physics in both cases is dust levitation, and so in one case we did these actual trajectory models, and we had an upward directed electric field above the illuminated surface and no electric field above the shadowed surface. So it's a very simple thing. And what happens is certain particles in that illuminated region can get lifted off the surface. If they've got any horizontal component to their initial velocity, then they're moving horizontally until their mass brings them back down to the surface, either because they're too massive to be levitated or because they move into a shadowed region. Since the craters have a shadow in them, they essentially act like a cold trap. So it's the same idea for how you get water molecules down into a permanently shadowed region on the moon or Mercury. If things are moving around, if water molecules are moving around, eventually, if they're in a cold spot, they stop moving around and you have a net accumulation. For the charged dust, if you've got a shadowed region, if they're hopping around due to electric fields that are driven by photoemission, they'll hop around until they make their way into a shadowed region, a region which is more frequently shadowed than the rest of the place, which is these pond formation. And we modeled it a completely different way with a stochastic model using a Markov chain where we just said, I'm not even going to follow physics of charging, I'm not going to follow trajectories or anything like that, I'm just going to say particles hop. And when we do that, they also end up in those craters. So craters can act as a trap. Now it's It's not the greatest observational, data in the world, and there's all sorts of assumptions and simplifications made in those models. So we really need to know more about what's the charging environment, what are the contact forces between the particles near the surface, things like that.
The gravity difference, the difference in the length of the cycle, the diurnal cycle. I mean, that would imply that the moon, which doesn't seem to have much homogeneity in terms of mixing horizontally, there's fewer cycles. The gravity is higher, so the tops are not going as far. They're essentially maybe hopping in place.
Right. Yeah.
Right. As opposed to
You're having
asteroids
much
where
more local phenomena than global.
Yeah. Okay. Thanks. We have to go. That's good for me. Dave has a question. Oh. Yes.
You can ask questions. You can indicate in the chat box what your question is, and we'll read it. Or how do they signal where the speed's not there? How do they signal us that they want to talk? What is that? How does that work? Okay. So what? I'll repeat that so that you can hear clearly. There's a control panel, and there's a place for you to raise your hand if you want us to mic you so that you can ask your question via your own voice, or if you would like us to read your question, type it into the chat box. Either way, please join us in this conversation. Thanks.
Thank you. Okay, Tom and then Doug and okay. Well, okay, Doug.
Two questions on your dust ponds. One is, given the model you did, why are they flat? I would think that if you sort of randomly throw stuff in there, it would end up being a lumpy surface.
I'm going to wave my hands a little bit and invoke other physics, which would be seismic shaking induced by impacts. So the other model for even formation of the dust ponds initially was independent of electrostatic, was that you have downslope movement basically in the craters. So you have just downslope movement and things flow. There's a recent paper that analyzed the distribution and morphology of these barriers. I just impressed at the moment. It said that the distribution and morphology of the ponds was not consistent with them being created by seismic shaking. Seismic shaking happens, and that would be your level. In our simulations, we do not get that. We do not get it to the point of deposition. Just as you said, we get preferential deposition in different locations based on what the morphology of the craters. Then we would say, okay, put the dust in there, and then impact on the asteroid cause things to set.
Then
Not a great
your discussion of what the mechanisms are, do we see those dust ponds on the moon? Why not? Why or why not?
No, and I would say that it's just what Pamela was referring to. We've got a much larger gravitational field. In fact, the distribution of ponds on Eros is very heavily concentrated towards the ends of the data, where the local acceleration is actually about half what it is at the base. It's quite small, very, very small. We don't, all we can say is that's a difference between Eros and the moon. And maybe that difference is the explanation for why we see that phenomenon on Eros and we don't see that same phenomenon on the moon. But we don't have enough real data on what the strength of the electric fields are even on Eros.
And
I just wanted to emphasize again that settlement of the moon and asteroids is not possible until we solve this problem of the grit in the seal. If you think about it, the modern designs have the spacesuits on the outside, permanently and absolutely black with material, and then you have to crawl into the back, close the door, unbuckle it, and move away. That means there is at least a meter long seal around there that is currently exposed and would not last an hour. So the question is, what kind of a shield can you produce for that shield? And I'm just want to emphasize, we're not going to settle the moon until that is designed.
That's good. That'll be a topic that'll come up during design challenges tomorrow too. But I want to comment on some of the strategies aside from along with Carlos Calle's work, essentially, which looks at an alternating EMF pattern to cause the dust to flow because of the differences, the alternating differences in EMF. There also is I work with another group that came up with a controlled charging way of forcing the dust to move to certain locations by essentially forcing a surface to be uniformly charged. And you can probably we've done this actually with electrons, with low-level plasmodiums. It's very low voltage and low energy. And we think this is also related to the kinds of effects that go on that cause dust to agglomerate and form into planetesimals fairly early in the evolution of solar systems as well. It's kind of interesting. The other approach that people have talked about using is what's called Lotus materials. And that is materials that essentially have a fractal structure, and it's harder for dust to accumulate in those materials. It just can't get a foothold because the surface is so varying at so many different scales simultaneously. Then there's another group actually that's talked about using differences in magnetic susceptibility to collect dust. That probably is going to be that probably varies somewhat with the size of the dust and its composition. So there are 3 or 4 different approaches that people have pursued, and the reason it's not happening faster is because there was actually money available for this specifically at that technology when the Constellation program was active, and the plug was pulled on that. It's still very interesting and useful, of course, not only for the lunar surface but for asteroids as well. So that'll be a topic that'll come up, especially when we talk about this technology. Very important point.
This is way outside my comfort zone, but I'll just add a little addendum to what you said about the fractal surfaces. And one of the experiments that we're working on at UCF is on the early stages of decimal formation. We play around with a lot of dust particles and we want to image it. And so we're looking around, watching stuff together, things like that. And we have to have it in a vacuum chamber. And the dust wants to stick to the walls of that chamber, which obstructs your view of your experiment. So it's the same basic problem, dust sticking to stuff, and what do you do about it? And our colleagues in Germany, Jürgen Blum, and the company, came up with a solution that worked for that particular application of putting a nanoparticle coating on the glass surface. And so, since the particles that you're looking at are significantly larger than that nanometer scale, the contact area is so reduced between the dust particle that you're worried about and whatever your surface is that they didn't stick. What did he say? It reduced the sticking efficiency by a factor of 1,000 or something like that. And so that kind of it's still transparent glass, and so they're. I think that's probably the same basic physics as what you're doing.
Those missions know that one of the ways to control the charging, so we don't have differential charging, is they actually have an ion gun that produces ions. And essentially neutralizes the plasma causes a uniform field essentially for the system of the spacecraft. People have differential charging. So these are not, and some of these approaches actually are fairly old, but finding the right combination and the approach that's going to work right for the right material. We're talking about a spacesuit as opposed to a hard surface on a robotic device, for example. You might want to use different approaches. It's probably not going to be just one approach, but these are all really good points. So what I'd like to do now is I'd like to. Oh, there's another question.
Yeah. Given the complexity of the charging of the surface, one of the focuses is building very small frames. So we have the lunar PCL and the paradigm that we're looking at. So what is the risk reduction in a mobile platform moving across the surface to the electrons, and what level of risk exists, and how can we model and experiment to test that before we advocate for paradigm, we had some confidence that if you put an Apple cell phone with a camera, the cultural approach that these things can survive. And so related to that, obviously this is a complicated area where more information is needed. So what kind of miniaturized instrumentation can we put so that as we're traveling around or trying to travel around, we're learning more about that design?
That's actually one of the particular interests of Dream 2, which is another one of the serving areas, which is specifically talking about differential charging and the impact that will have on humans on equipment that's on the surface of the moon. And there's been some modeling done about what happens on those craters as the relative amount of shadowing changes and the thermal conditions change. And there's two aspects of it. One is monitoring and one is preventing. The first approximation, we need to sort of model it and then basically test the model by actually providing some measurements of those devices. It's important to point out, which the astronauts actually, I was at a microsymposium at the Lunar Planetary Science Conference a couple of weeks ago, and it's important to say what the astronauts say. We had two astronauts there, Dave Scott and Harrison Schmitt, and they will point out to you that they were on the moon, they knew nothing about charging on the moon, and they did extremely well, and there was shadowing under the lander, there was shadowing under the rover, they stood in the shadow of boulders. There were no catastrophes, as we know, aside from abrading the space suits, because they were trying to brush the dust away, and it was extremely rough. It's like shards of glass, actually, at a very small scale. They didn't have any serious issues. So it's important to keep the context here. Yes, there are issues, and there's differential charging, and it has to be dealt with. And we are going to go into environments that are far more extreme than the astronauts were in. The first approximation is not absolutely catastrophic, but there are lots of that we've developed actually. We'll talk about these also. Some of these instruments that are very compact that flew on the LADI that can provide built-in particles measurements in situ, and they're extremely compact and they're easy to fly along. They're little things that you can put on the tires or the bottoms of the soles of spacesuits that can look at things like electrostatic charging and synthetic susceptibility variations that people have actually developed and tested in the laboratory. So there's potentially lots of different ways of actually monitoring the environment. And there's also a lot of proposals for what we can do that involve potential CubeSat missions that could, for example, send a series of a sequence of impactors to actually impact a crater and look at what happens in the way of measure basically what happens in the way of how fields get redistributed, how the charging changes, what the particles generation is, both in terms of dust and charged particles, and what kind of follicles and simple molecules are actually stirred up. And these are proposals that are on the table. So there's lots of proposals to actually look at the result of these, what could be the result of an impact event, or some kind of a disruption. It could be human or it could be a natural one, but that could potentially disrupt the existing charging field. Definitely. Russell.
So I want to go back to my earlier question about getting lost. It's a slightly different question. So the idea is, one of the, when this first came about, one of the things I was looking for was unique solutions, unique applications of the chemical space. And so one of the first things people talk about is infrared telescopes. It's got a 40 Kelvin ambient temperature. It is permanently shadowed with lots of stuff around it. One of the things a lot of people say is, oh, but the dust is good. So your telescope ambient shuttle on the mirrors and light is terrible. I think since then, looking at some things similar to yours, that in fact it's credible to believe, that's why I was saying about like a 1 kilometer sized crater, you're going to get extra dust that's going to fall at the edges, but at the center of it, one, it appears there's not all that much dust going to fall to begin with, the other is, in the center of a permanently shadowed crater, there could be even less. And so one might be able to embed this whole idea that dust is just going to
That's an excellent point. To whatever degree, based on our current, admittedly limited understanding, the mobility is enhanced at light-dark boundaries. And if your crater is large enough, then if you're well away, if you're well within a permanently shadowed region so that you're never near any sort of boundary, then there'd be no particular mechanism, no particular reason to expect this mechanism to be delivering dust to where you are. There's other things going on, but yeah, you're probably in a pretty clean environment, all things considered. That's a good point.
One quick thing, that could be an interesting place for some people, not myself, to look at as far as what kind of measurements could be made that would support or worry about an IR telescope.
Should we put the questions up while we have this discussion so we'll kind of bear them in mind? Because we've been addressing various aspects of the questions.
I'm gonna go back 2 questions and just about the technology mitigation. And one of the things that we should bear in mind is we have all sorts of experience with working in dirty environments on Mars. And Mars is very dusty, and the atmosphere is both a helper and a hindrance. So it delivers dust in much greater quantities than any of these, like the electrostatic stuff that we've been talking about, or meteoritic hardening, or anything like that. On the other hand, it also blows it off. So with the Spirit and Opportunity rovers, they've got a big accumulation of dust on the solar panels, and the output of those panels went down precipitously. And that dust was delivered by dust storms, atmospheric dust phenomena. And the wind comes along and blows it all off. But independent of that, those rovers are going around, they're digging little holes in rock and stirring up dust and things like that. And so they're actually, we do have some non-negligible mileage, if you will, operating various sorts of scientific instruments and machinery in dusty environments. I don't think there's, like Pamela was saying, there's not one solution that takes care of everything, but we do have some experience with.
It's important to point out, and it's important to point out that on Mars, on Mars, all the way that we treat the samples to date, where we essentially grind up samples to get compositional information, that does introduce a contamination factor, which I believe strongly is related to the dust. The dust can be differentially coating the insides of the chambers where the sampling is actually taking place. So we're seeing, I think, a homogenization effect. But unlike the moon, I think there's actually a homogenization of the dusty surface of Mars too. So you don't necessarily see the distinctive geochemical boundaries on Mars that you do on the moon. The moon is such a nice target in so many ways. But taking care of that problem, actually being able to have a sample that is in a pristine condition, that you're not contaminating yourself with some of the newer instrumentation. I'm working with a group that's proposed to develop a combined X-ray fluorescence, X-ray diffraction instrument that does not require any sample preparation. This is basically align itself above the sample, take direct compositional measurements, map the elemental abundances, map the mineralogy, and essentially when you can do that, you're mapping the rock, you're actually looking at its history. So you can actually get an assessment by looking at the mineralogy, elemental abundance, variation, plus the crystalline structure and the orientation of crystals, without actually ever touching a sample of an entire history of a rock. And of course, naturally, like everybody else, I'm going to complain that we haven't gotten any money to really push it forward because we're competing with CheMin, which is the existing old technology combined with X-ray fluorescence and diffraction, which requires sample preparation. You have to grind up a sample, you lose all of the primary information on that sample, no longer know how the minerals are distributed or the elemental abundances are distributed, and you can just basically do an average for the entire sample. The old approach, that's required, basically you have to have a randomized crystal structure. The newer approach, there are tricks you can use to get around having to do that. So it's things like this that actually give you so much more information in situ, and if you could make the argument, I'm going to take an extreme position here, that it would be far better to develop in-situ instruments that require minimal amounts of sample handling than to collect a sample. I'm going to leave it at that. I really believe this. That collecting a sample is so challenging when humans are not in the loop. And we talked about that 2 weeks ago too, how the extraordinary ability that the astronauts had to sample, to selectively sample. Anybody can pick up a bunch of samples. But to pick up samples that were truly representative of an entire region around the sampling area is a non-trivial capability. And until we have that in place, I would make the argument that in situ measurements of all kinds that require minimal disruption of the environment are actually far superior than just a grab and go for a sample. But this is heresy. I want to touch a little bit about if you look at the decadal surveys, which we always have to do when we're writing proposals to a science mission directorate, you will find that despite the fact that they don't actually mention they don't mention CubeSat Class D missions, and they do have specific missions that they mention that are Discovery Class or above that are essentially Class A missions. But in terms of the science that is applied that people want to get done, which is looking at whole systems, being able to look at dynamic changes, temporal and spatial variations, all the justification for doing multi-platform measurements with small, basically with these differently or identically instrumented standard buses is there. If you read between the lines, there's a constant between the lines saying, well, wouldn't it be great if we could do this? But of course we can't do this. But we know the answer. Yes, we can do this. This is what this opens up with the possibility of inexpensive platforms that have standardized with standardized interfaces that you could do many of to sample your environment much more systematically than doing a single Class A spacecraft. I mean, there's all kinds of possibilities that are opened up. We can't even approach now with the models that we have in place. I'm hoping that with Discovery Class, we get a foot in the door by having Discovery have an option for Class D proposal. I can't guarantee that's going to happen this time around, but I worked really hard with as many contacts as I could possibly use to convince the people that actually do have influence the possibility to do with that in the instrument development program. I think in the instrument development area, we're actually going to get a separate instrument development category for CubeSat instruments within the year. I think that that's actually going to happen. So going back just to the questions I want to continue the discussion. I just want to mention that we have been talking about what information is lacking in understanding of the lunar surface and what measurements can be used to fill in the gaps. We've started to address that. What is the nature of future investigations and methodologies that should be carried out to further our understanding of the lunar surface, and where and when should these take place? And by the way, to me, that also involves theoretical measurements, analytical determinations, laboratory measurements, as well as actual observations in the field. And what measurements or investigations do we need to investigate a range of models for space weather and regular formation and the role of organics? These are more specific questions. So I want to make sure that the speakers have an opportunity to also address these questions from your, because I told you to think about them a little bit. Would you like to take a stab at?
Sure. Well, on the first question, from my science area, I was talking about some of the stuff that we didn't get a chance to talk about, which are some mechanical properties of regoliths. And we have a lab at UCF, the Center for Microgravity Research, where we do mechanical experiments with simulated lunar regolith, asteroidal regolith, as well as protoplanetary dust to look at sticking, cratering, ejecta, things like that in low gravity environments. And so we've got monoconic halos, we do lunar parabolas, as well as zero-G experiments. So for all of that, and it ties in with what I was talking about earlier, one of the sort of the fundamental questions is what's the sort of granular flow dynamics for lunar regolith? How does the complex shape of the size distribution of those particles affect its mechanical response to the kinds of activities that take place in both manned and unmanned exploration? So, simple example is the Apollo astronauts trying to take core samples, and you can't get through that. It's very fine dust, but the way it behaves, it compacts itself very well, becomes very rigid. So how do you excavate? How do you deal with that. On the more related to what I was talking about earlier with the charged dust dynamics, what are the forces necessary to separate particles? What's the size distribution of the particles in the upper layers, the upper millimeters, say, of the lunar regolith? How does that vary with lunographic location? So is it different right at a crater rim than it is at the crater floor? How does it vary with latitude? Things like that. So all sorts of measurements about the mechanical properties and the variation of those mechanical properties of the dust particles on the surface of the moon. And the other measurements are things that what Addie was talking about is the charging properties in the plasma environment. So she mentioned Langmuir probes, and these are difficult to measure the very low density plasmas that you would have near the lunar surface, but that's something that we really need to know, is what is the electron density in the 2 meters above the lunar surface where people would be walking around and equipment would be walking around. So we don't really have a good idea on that.
So do you have a vision of what one of these Langmuir instruments might look like?
Oh, Langmuir probe is a very simple instrument.
Cool.
Yeah, there have been a few people. I worked with a group in Colorado for a while, and Langmuir probes are just basically some sort of metallic surface that you stick into a plasma, and then we measure the current of the surface. So the important thing about that is, though, that you have to understand what your relative grounding environment is, and what your potential distribution is going to be.
So you have to sort of have a theoretical model of your surface ahead of time to capture the essence. For example, if you were putting one of these on the moon, what you'd expect for variations in
to some extent, but you also just need to know how your instrument is going to respond. So a lot of the sort of Langmuir probe models for the moon have like a double probe, so you have 2 probes, and that way you can actually sort of understand the differences in the potential.
So you could have left and right.
Yeah,
Vertical,
sometimes vertical,
left, right.
sometimes left, right. Yeah, and if you can get it at different heights, then you can understand. It's just wires or a sphere.
So this is cool because this kind of thing, the just wire part, lends itself so nicely to the deployables people are developing for CubeSats.
Yeah.
So you can just simply send out these wires
Snap
from
out a little boom or something.
Yeah.
And it can be a sphere or a wire. You model it differently depending on the shape of.
It could be a sphere. Could be a spiral.
It can't be a spiral, but a sphere at the end of the probe.
You want something that's collecting electrons or ions from the plasma, and so you put some conductor into that plasma and you try to separate the charge collecting bit from the rest of your circuit, which would be ground. And that's, so ground could be a big spacecraft, or it could literally be ground, or it could just be, I've got another plasma collecting element in some other location. So then I'm just measuring the potential difference between those 2 points. So the sphere would be like a golf ball at the end of a rod.
So say if you, I'm thinking about a concept where you might separate 2 stations, and you could get measurements on either side of a terminator, for example. If the electric is
connected. You could take measurements in both locations, but they would have to be, and compare those measurements, but they'd have to be calibrated.
Could it be the lunar ground? It could be the ground. Well, that's true.
Yeah.
Yes.
One other procedure for that, which Jack Burns has talked about quite a bit, is if you receive low frequency radio waves from the external world, the cutoff on that is the kind of cutoff that you get with the ionosphere, and that gives you a measure of the ionosphere on the surface of the moon.
A couple of quick points. What's sticking the fine particles to the surfaces is called van der Waal forces, and they actually come from the physical mechanical forces at extremely low levels and have a 4th power, I think, distance effect. But there is a very rich literature under contamination, not rather than under this dust, that you can get to, and I think it's far more important to understand where electrostatics takes over from van der Waals than it is electrostatics to gravity.
I think you're right, actually, and I think that van der Waals, what's going on in the early nebula formation to form things before they get to a size where gravitational dynamics can explain what we're seeing. There's a huge range in there between the initial particles and then things that are essentially planetesimals that are large enough to measure in the order of, let's say, a kilometer or so in size. It probably has a lot to do with van der Waals interaction, a very low gravity environment, as well as the kind of charging that's going on in the solar nebula.
Just to clarify, all the gravity stuff I talked about is once the particles are off the surface, right? The separation depends on the contact forces.
And some work has been done to try to start looking at some of these contact forces. So one of the slides I showed looking at passive mitigation techniques, and one of the things we did for that was try to understand the contact forces between the surfaces and the lunar simulants. Obviously that wasn't with real lunar grains, but similar things can be done with real lunar grains. And there has been some initial work trying to look at what those contact forces are in the laboratory. So it's a fairly complicated measurement to get if you're trying to understand lunar grains or even lunar simulants. But people are starting to look at that because it is recognized as very important.
One other quick point. You talked about rovers. The way rovers fail is that the wheels bind up. The wheels bind up because the dust gets through the seals into the bearings. So the seals on a shaft, rather than a thing, are another absolutely critical, this is going to kill us if we don't solve it problem.
So is it possible that if you were to that you could imply the role of van der Waals forces without measuring them directly by the way you set up your experiment?
Yeah, so both in experiments and in models, sort of pivot and keep in more
Right.
To say, okay, what's that sticking force we have to overcome? But again, we need to have some sort of understanding of what that can be. And there is a large body of literature in terms of the largest body of literature I've seen is actually exotoner particles, because since Xerox, obviously, very important, very interested in understanding how particles, very fine particles, fit together. So a lot of the literature is from companies like Xerox who have tried to understand particles to each other and to other systems.
This is why collaborative efforts are so important, really,
Yeah.
because I'm thinking that if you are designing some way to effectively mitigate dust, and you need to, of course, perform a series of laboratory measurements, and then, of course, the ultimate test is in the environment itself, whether something is working, then that's going to have implications for van der Waals forces and the role that van der Waals forces play. So it would be nice if you're actually working with people who know about the theoretical modeling, as well as people who have to solve the problem, and all of them in the room to actually be thinking about that, and looking at the implications for how effectively different mitigation strategies that you might be trying out on the moon with testing various hypotheses actually are working. This is a really important area. It's a nice area because it's where all these things come together. The need to do the engineering properly so that you can survive in the environment with equipment or people, the understanding of the environment itself, and of course all of these things. I mean, one of the reasons I'm interested in them is because I believe that the interactions between these regoliths, charged particles, dust particles, in the presence or lack of presence of plasmas and volatiles, has everything to do with planet formation and probably the origin of life. I really believe that. I think that there's obviously one of the things that Dan Britt talked about, which I was hoping if he was here he would talk a little bit more about, that he talked about at the Lunar Planetary Science Conference, was things that could be happening with organic materials. There are reactions that organic petroleum chemists and other organic geochemists study that involve these reactions that take place, polymerization reactions that produce hydrocarbons. And of course, the conditions under which we like to form long-chain hydrocarbons probably don't exist on these asteroids, but what does exist is simple molecules, hydrogen, carbon, oxygen, that are interacting to potentially even produce water, as well as carbon-hydrogen compounds, potentially very simple ones. But of course, the question is, what kinds are of these, and what do we have? Because we have an environment with things that they don't want to exist. They're called Fischer-Tropsch reactions, and we don't want to have things like sulfur around. But they're around on asteroid surfaces. They're around on the surface of Mercury. and other things too. So the question is, this is a very interesting area because it's going to tell us something, I think, about the biological precursors that we could potentially be forming, and it has implications for water because water is a product. So if these are efficient reactions, and you have water being produced, you're effectively potentially self-limiting in terms of how much water can be produced and when it can be produced, because you're pushing that reaction back in the opposite direction. So these are all really interesting things. I think that I have been a chemist. I actually have a PhD in chemistry, so I'm thinking there's probably a Nobel Prize in chemistry there somewhere for people who can actually figure this out. But all of these things, I mean, the ability to provide in situ measurements that can give us a clue as to any of these things without worrying about the contamination. You know, this is a big issue when we took samples back from the moon. The moment we removed them from their environment, the contamination process began. One of the first things that happened is that they became coated with water. Because even the environment, even in those boxes, sealed in those boxes, when the astronauts returned them to Earth, the interaction, the degradation that took place at the very surface of these samples, started to happen. So I'm a big fan of figuring out any ways we can to get in situ measurements. And of course, this is a challenge because it's one thing to say we're going to have compact instruments that'll fit into a CubeSat volume format. But it's a whole other thing when you have to start figuring out what that trade space is that's still going to give you sensitive enough measurements. But fortunately, there's a lot of, I'm not terribly knowledgeable about this, but there's a lot of work going on in MEMS devices that can provide in situ measurements with fairly high sensitivity, for example, for mass spectrometers. And so I'm hoping that we can, by opening up a possibility to look at compact CubeSat instruments, we're actually going to be looking at some of these really small format things with very new technologies that could give us nice, in situ, very sensitive in situ measurements of things at the sort of trace level. Do you have any comments on that, Adrian?
I don't have as many comments about the organics. I did want to sort of tie together a lot of what Tom has been pointing out, is that there needs to be a lot more research into dust interactions and our understanding of those. And you're preaching to the choir. I definitely agree with you. And Camilla mentioned earlier that there was a dust analysis group that had been established with the Constellation program. That was actually, their funding was cut. But there are groups around the country and sort of independently working on a lot of these problems. And we identify that it's a big issue. So I don't know if this is something where more collaboration can happen with industry or with smaller partners. But we're definitely interested in doing some of these studies. So if we can find better ways to do that.
I'll just follow on to that very briefly. There was a group led by me and Jennifer Curtis at the University of Florida. She's the professor in the chemical engineering department, to look at dust mitigation technologies. And they've got a particle something center at UF that developed nanofiber filters for dust filtration, because there's not just coating on the seals, there's keeping it out of the respirable environment in wherever an astronaut habitat is, and all sorts of issues. So as Addie's just saying, that's a local here in Florida group that has done a lot of sort of technology, investigation, development, characterization of dust, dust samples.
Yeah, I've talked some to Larry Taylor at the University of Tennessee at Knoxville, and he is always interested in nanophase iron and the impact. And of course, in very mature soils, there's a higher concentration. I think there's some association maybe with high titanium basalts, but in more mature soils, I think you get more of this nanophase iron. So is that something that has been part of your sampling process in the analysis of samples? Have you had that kind of material, and have you used these magnetic potential mitigation or cleaning processes that he's talked about that may have some potential for improving the dust mitigation?
So most of the simulants we've used haven't had the nanophase iron. That's a relatively new component that people are starting to include. You mentioned earlier that there's some new simulants that have different composition, and that's part of it, is including this nanophase iron.
I think he's making some, yeah.
Yeah, and as you might expect, if there's an iron component, that's going to have a very different reaction than most of the insulating properties of the rest of the thing. I think, did you have an instrument that was sort of a magnetic dust mitigation, or idea for a magnetic dust mitigation? Who was developing that?
Well, actually, I worked with a group that was led by Steve Curtis at the Goddard Space Flight Center that was looking at yet another approach to removing dust, which was based on very low watt, low voltage charging, and it has implications for conditions that could exist in the early solar nebula that would essentially uniformly charge dust, so it would create an environment where dust was either repelled or attracted. And yeah, we were working. And actually, we had Carlos Calle was also a collaborator with us on that. So yeah, the nanophase iron problem is interesting. It actually came up when Dan gave a presentation at the Lunar Planetary Science Conference about what the role of nanophase iron is. Now, it appears that if you look at Mercury, for example, one of the reasons they're having a hard time explaining the discrepancy between what the spectral reflectance data are implying and what the direct elemental abundance is derived from X-ray and gamma ray spectrometry are implying is because the way space weathering occurs and the specific role of nanophase iron and the role that, for example, sulfur could be playing, and that implies that there could actually be a role for small, simple organics in looking at. I mean, sulfur by itself is a very odd thing optically. Sulfur causes very extreme optical variations at very small abundances, and there's plenty of sulfur according to the elemental abundance calculations on Mercury. And then the abundance of titanium is actually very different on Mercury than it is on the Moon. And then when it comes to asteroids are different from planets. I mean, they have a large amount of metallic iron in comparison, plus a lot of sulfur. And there's a discussion of what happens to that metallic iron, because it doesn't behave like silicates when you have micrometeorite bombardment or a large impact. There's going to be differential melting effects, and there's a question as to whether the metallic component ends up at the top of the regolith or the bottom of the regolith. Where does it actually end up? And is that one of the reasons that we're seeing differences in Class S asteroids? Because it depends on what the overall elemental abundance of iron is and where it actually ends up, and that is going to affect the weathering of individual particles, of course, as well as all of the overall composition. So the truth is that although we have a lot of lunar samples to look at, and that's very good, but by itself, it's not going to completely reveal what's going on in the way of surface interactions, which is actually good. I mean, there's lots more questions about how space weathering occurs
This is
when you have
another
very different surfaces.
This is another very fruitful area for ideas, experiments, and going to the lunar surface and answering these questions for other airless bodies.
Yeah, so the second question that we have up here is like when and how should we do these studies? So I think we've been talking a lot about different experimental studies we could do here. We talked about putting Langmuir probes on the surface, and the nice thing about Langmuir probes and other similar types of probes is they are very small. They can be very small and could be tied to some of these upcoming missions, I think. I do think it's important to try to understand the lunar environment before we start sending a lot of stuff there. Because as we've mentioned, well, I don't know if we've mentioned this so far, but any surface activity is going to generate more dust and stir up more dust. It's going to significantly change the atmosphere above the lunar surface. So it's very important to sort of understand these conditions now before we have a lot of development. And so maybe that can be something where a lot of these small missions take plasma instruments or dust charge instruments. You mentioned there are some very small little ways to measure triboelectric charging, especially on dusty surfaces. And so those can be used on rover wheels, little probes that stick out from rovers. So there's lots of ways to include that on CubeSats or small missions.
You know, it seems that your argument is that there should be a range of small precursor electrostatic dust-related kinds of explorations before we have larger commitments, you know, to bind down the risk of burn.
Yeah. And I know other communities, not just the dust community, but other communities have interest in understanding the lunar environment before we change it completely also.
Especially if we're thinking about getting into the cold traps. I mean, we're talking about essentially looking at things that could be recording events that happen on the moon over time. Where does this stuff come from? Does it really come from relatively recent cometary impact? Has it been there for a long time? I mean, things like the kinds of instrument measurements. One of the things I keep mentioning mass spec is because one of the nice things that mass spectrometers can do is it can look at isotope ratios. And if you can look at isotope ratios, potentially, I'm not saying this is easily doable, but there are people that propose state-of-the-art technology that involves looking at selected isotope ratios, for example, to get geochronology information, systematically all the reasons for collecting a sample because of the technologies that have recently come online in an effort to make them very compact are being removed. In other words, if we can get in situ measurements that will allow us to date the age of a sample, if we can look at isotope ratios in the sample for various isochrons, especially if we can look at things like oxygen isotope ratios, carbon isotope ratios. Then the reason for removing a sample from that environment, providing you're documenting it really well, it starts to disappear. And that means that you could potentially, to make this work at the CubeSat level, you can do a couple things. One is, when I think about the nice idea of having a distributed system of CubeSats, distributed in orbit, distributed on the surface, distributed in time, distributed in space. So sequential impactors, stations in orbit and on the ground, so that can essentially record phenomena from different standpoints. There are instruments that are available now, like the fields and particles instruments, even spectrometers that could give us that kind of information. The next generation challenge is to make instruments that can do the kinds of things I'm talking about, detailed compositional information, without resorting to sample handling. Basically, by pointing an instrument at something, and maybe put something like the laser ablation technique, for example, for differentially looking at a sample and looking at what happens when you vaporize it in a small area. And you can get isotope ratios, and you can get potentially geochrons that allow you to date samples. If you can do that at a location, of course, one of the big challenges we've talked about here, implied here, is robotics, mobility. It's going to be difficult to solve those problems without dealing with dust and power. The other big one, of course, which we'll talk about more later in the meeting, is power. And the big one there, from my standpoint, is batteries. Batteries are our stumbling block at the moment. There are technologies that look promising, but getting them, funding to develop them up the TRL ladder is kind of challenging. And I know that the folks at JPL that were doing a lot of work on the lithium-based technology for batteries have had significant reduction in funding. And I don't think that radiothermal generators are the answer personally, because of the extraordinary amount of money involved in developing them and the security issues revolving around using them. So I'm not that keen on that if we can find alternatives. The other practical problem is that there just isn't plutonium-238 available at the rate that we'd like it to be available to support robotics missions. So that's going to be an issue. So solving the power problem and the dust mitigation problem for mobile structures. Structures have to operate in a cold, dusty environment. If we can do that for the moon, on the other hand, where the conditions are relatively extreme, I believe we can do that for asteroids. The moon is a nice nearby target where we can test out a lot of these things. Those are some areas I look at in terms of the kinds of things I'd like to see. I'd like to see multiple platforms on the ground and in orbit with simple instruments that can give us monitoring of the lunar environment. And the other thing that Russell might want to give more details on is another possibility that recent indications are that there's a population of objects that are extremely small that are traveling through the solar system and periodically visiting us through the Lagrange points. And these have been called mini-moons by Bill Botte. And these objects could potentially, it looks like many of them are heterogeneous, which means they could be fragments representing different places and times in solar system history. It could be very interesting to look at. And ideal observational standpoints are the Lagrange points themselves. It's because they enter and depart through these Lagrange points, which are relatively easy to travel between along these what are called weak stability boundary trajectories. So another interesting class of things that still in cislunar space at the Lagrange points would be observatories that would sit at these places and observe these objects and potentially track or follow them. Yes, Dave.
It occurs to me, especially with asteroids, that if there's electrostatic charging off the surfaces, then potentially this is a way of sampling the body and collecting the dust without being, having to land and be in contact or anchor or impact. And I wonder, have you thought much about dust as a sample resource or as a way of doing a precursor sampling missions for those kinds of surfaces.
Well, I hadn't thought about it directly in those terms. So OSIRIS-REx is going to go blow a little puff of gas onto the surface of their asteroid and have some dust blow back that they'll capture. I have, I guess, some indirect experience with that from Galileo, Jupiter orbiter. I had a dust detector on board. It's basically a salad bowl that detects impacts onto it. And we were able to show that some fraction of the particles that it impacted were captured retrograde dust grains, so not interplanetary and not part of a prograde population. But when the quantity is probably so low. I mean, it would be great to have a nice, big, large area dust detector on some asteroid orbiter or something like that to see what sort of environment you've got. You've got to distinguish the particles from the interstellar interplanetary dust flux as well. I don't know what the flux would be like. My gut tells me you'd have to get so close to the surface to get a reasonable amount that you might as well go do what OSIRIS-REx is doing anyway.
So maybe looking at the dust holes produced by dust or impact rates on solar sails near an asteroid would...
Yeah, there's been some dust impact studies on space shuttle and stations. The LDEX instrument, the probe being doing right now, is sort of using this, what you're talking about, but they're getting low impact rates. Like they're not expected to get sizable amounts of dust. They are detecting dust that's being wafted up the surface, and you can add like composition measurements to that as well.
It's that I was just going. The last thing I was going to say is there's a difference between detection and analysis. And so these things have to come in and splatter, and then you collect with a mass spectrometer, everything. And Cassini's got one of those, and boy, it's just tough. And they have probably a lot more dust to work with in the Saturn system with the rings than you get an asteroid. And it took 10 years for them to put together enough particles to say something composition. I mean, it's just, yeah. I mean, when they were flying through the Enceladus plumes, those geysers, they were able to do a compositional analysis because they've got the real flux. But there's not going to be anything like that in what we've been talking about.
Yes.
There's another process that this question suggested that I could bring up is the Artemis mission has a process where they take the pickup ions, and so they can tell where on the surface these ions came from. And so that's different than dust particles. It's another remote sensing technique and then that becomes questions, can you do something similar around an asteroid where you could, at a distant kilometer or something, be talking about things that are getting sputtered off the surface and you can say something.
Yeah, so that tells you about like you said, the sputtering off the surface of ions and electrons, specifically ions. And that will tell you a lot about the potentials above the surface and the electric fields above the surface. So some of the results from the Artemis mission are showing that there's these interesting potentials that are probably accelerating ions out away from the surface. So that's definitely something. Artemis is sort of a fortuitous mission in that it was a solar mission that then got two of the probes got repurposed to go around the moon. But you could put instruments like that on orbiting spacecraft.
I'm betting if you could hook yourself onto an asteroid some way, you could just detect the trailing dust, as well as its composition. It's fairly simple instruments.
Good, thank you.
Any other burning questions? I think we're about to, we have 2 minutes. We have 2 minutes. We have time for a short question. I didn't mean to do that. But I think this has been very fruitful and productive. We've really covered all the territory in those questions. Looking at the interesting science that needs to be done, kind of investigations we'd like to do, and potential general concepts and ways we'd like to, basically what we'd like to sample, where we'd like to go. And in the afternoon, we're going to talk about some more concrete, specific concepts for actually getting some of these measurements.